Thank you, Peter, and thank you, everyone, for coming to this afternoon. I have a lot of things for you today. So, yes, I'm Ittai Abraham from VMware Research, and you can check my blog. Some of the content of this talk will eventually go to that blog as well. Okay, so what do I plan to do today? I plan to talk about things related to Byzantine fault tolerance. I'll start by explaining this primary backup replication paradigm. This is something that's not new. This goes back to Barbara Liskov's view-stamp replication and Lamport's Paxos approach. And then I'll kind of show how you can start with omission failures and move from omission corruptions to Byzantine corruptions. So this is kind of a way to start with a protocol that's resilient to omissions and move to Byzantine failures. This is kind of inspired by the famous Dwork Lynch Stockmeyer paper and PBFT, Practical Byzantine Fault Tolerance. And then I will show how to take these protocols and move from synchronous models to partial synchrony to maybe a sketch of how to move to asynchronous models. And this is going to be based on more modern work. Some of it is also mine, so Tendermint, Casper, and Hot Stuff and Vaba, which I'm involved in. Later on, we will also see how we can take the same basic protocol and move in the synchronous model from a standard primary backup approach to an adaptive algorithm. And this is based on work of Katz and Koo and some of my recent work as well. And then we will talk about how to move from a single-shot consensus to what's called state machine replication. As you know, state machine replication is what everybody is interested in. Again, this is actually a lot of the core ideas here are not new. This goes back to Lamport's work from '78, Fred Schneider's tutorial on state machine replication, and again, more work that Barbara Liskov and her team did in the early 2000s. And finally, I will talk about blockchain. So usually I talk about this at the beginning, but here I want to start kind of telling you a lot about protocols. But actually, all these protocols are connected to this later results. And if I have time, I will talk about that and Nakamoto's paper and how it's related to all this stuff above it. Okay, so yeah, this is the plan, assuming we have a whole day. I probably won't have time because I just have 3 hours with you. So I'll have to feel you and see where we want to move faster and where we want to skip and so on. But that's kind of at least my ambitious plan. Okay, so what's the approach for today? So the traditional way I learned distributed computing is by basically learning different islands of protocols. So you learn some asynchronous protocol for binary Byzantine agreement. You learn Paxos protocol. You learn some lower bound. And what I want to try to do today is expose you to a modern view that I'm trying to build, where we're trying to take all these protocols and find some sort of connecting foundations. And the reason this is nice is because once you understand how things are connected, you can build better abstractions, and that gives you sometimes better protocols, better systems, and so on. Okay, so this is a big area, and there's a lot of things to learn. Some of you here are probably masters and experts, and some of you are new to this area. So I'll say a few things about what I hope you will learn from this talk. So my approach is to first give you the right intuition, and then give you the right rigor. So in a sense, I believe that you first have to understand why what we're doing is what we're doing, and then there is a lot of rigor and details around it. So I will focus first on intuition, but note that you cannot do this without also understanding the rigor and all the gory details of these protocols. I'm a big believer in learning by asking, so I really want you to stop me and ask questions. I will be offended if you don't ask me questions. It's as if you're not listening. So even if you don't have questions, try to raise and answer questions just to make me feel happy. I believe in learning by doing, so the fact that you just are listening to me will not help you learn. If you really want to understand, you have to do research, you have to build software, you have to try these things by yourselves. So again, just hearing me is not enough. Yeah, and this goes back to this idea of there's no shortcuts. So at the end, there's a lot of rigor and details behind this talk that you will have to go and understand, explore yourself. You will not have time in 3 hours to do all of that. Okay, so let's start, and I'll start by kind of very quickly defining this notion of consensus, which you've already probably seen in this week, right? So consensus is kind of a voting protocol for making decisions. So basically there's a group, they want to make decisions, and they each have their own opinion. So here we'll assume that there's some initial input, and this initial input is authenticated. So there's some way that this initial input is signed, and we can verify the signature. And at the end of the protocol, what we want is everybody to make a decision, right? This is the termination definition. And really the kind of core thing about consensus is that we want to have this property that we all decide the same value, right? We don't want to have a disagreement. And this is the kind of a safety property, the famous safety property. And then you add an adversary. So you say, well, because otherwise it's not interesting. So you add some adversary. Maybe this adversary can corrupt nodes, can cause them to crash, or to do emission failures, or Byzantine failures. You also add some networking model, maybe synchrony, asynchrony, partial synchrony. Any of this is surprising or new to you? I mean, assuming you've heard this week, this should be very new, right? Good. I see one person nodding. Yeah. So this solving this is trivial, right? So why is this trivial? Because? No. You can just decide nothing. Okay. So one way to all agree is like maybe decide like on nothing. So basically what I want to say is that you want to have termination and safety, but that's not enough. You also have to have some sort of a validity property to make Byzantine agreement non-trivial. And so, to make the problem non-trivial, you add a validity property which says that if all the honest have the same input, then this has to be the decision value, right? Otherwise, let's say, we're trying to do a binary agreement between 0 and 1, we can always decide 0. No matter what happens, no matter what the inputs are, always decide 0. So no matter what the adversary does, you just decide 0, and so we all agree with each other. But it's kind of less trivial. And so we want to have this validity property, and this is kind of the validity property that Lamport defined in '78. And this actually turns out not to be the only possible validity property. There are stronger ones, and they're going to be important for us, and more powerful because you can build from them better types of constructions. In particular, what we'll want is this a stronger validity property that says that, well, we all have some authenticated input, and with constant probability, the decision value that's chosen is actually a decision value that comes from one of the honest parties. Okay? So note that we don't have to have this property that all honest parties have the same value. Right? We might all be honest, each one of us has a different value, and we still reach agreement on a non-trivial value. All right, so this is kind of the definition of consensus. And I want to extend this to the client-server model because, again, in kind of this Byzantine fault-tolerant state machine replication approach, there are servers that are maintaining the state, and then there are clients that are sending messages. This is the same as, like, in Bitcoin, you have miners that are maintaining the state, and you have people sending transactions to these miners. It's kind of a client-server approach. So this is kind of the client-server approach. Again, clients only talk to servers, so clients are kind of stateless and don't have power. They can send authenticated messages, so clients can sign commands. And clients themselves, we have no assumption about their resilience. So they might fail to send messages, and so on. So they can have emission failures. And the goal of servers is to kind of commit to a request. So basically, there are clients sending authenticated requests, and servers need to agree on a command. And what the clients need to do is learn which command has been committed, right? So if the command is, let's say, I'm paying Peter $1 million, then people have to agree that I paid him and maybe not Eli. And so, this can be used to create a sequence of committed commands. This is kind of the state machine approach. And for this talk, I want to focus on like this abstract single shot case. So there are clients and servers. The servers have authenticated input, and I'm basically assuming that this authenticated input came from these clients. And what we want is kind of these three properties, right? So termination, where eventually everybody agrees. Eventually everybody has to decide. Safety or agreement, where we all decide on the same value. And these validity properties, so I mentioned here two of them. One is the traditional validity property, and the one that I'm going to focus on is this stronger version, which says that the input of the decision value is coming from an honest party. Okay, this should all be relatively known to you and not surprising. So anybody has is anybody surprised here or has any questions about this? I see one person. Okay, that's good enough. Okay, two? Okay, good. So let's talk about primary backup in the emission model. So we're going to build the primary backup in the emission model. That's basically, a variant of Paxos. So the emission model, there's n replicas. The adversary can corrupt f out of these n's. And corruption by omission, you know what that means. It means that the adversary can block incoming messages or can block outgoing messages, and it can do it adaptively. So it can decide which messages to block, which messages to pass through. That's the kind of omission. And the approach, the primary backup approach, is an approach that works in views. Okay, so we'll have a sequence of views. Views move like natural numbers, 1, 2, 3, and 4, and 5, and so on. And every view, there is a designated primary, and all the rest in the view are backups. Every time we move a view, we might have a different primary. And there's many ways to decide for a given view who's the primary. We're going to use for now the simplest version, which is the primary is just, let's say, some rotating coordinator. So let's say, in the primary in view I is just mod, I mod n. Okay. There's many other options. As I said, you can use randomized leader election. We'll talk about that a lot more maybe in the later parts. You can use backup protocols where people want to try to say, I want to be a leader, and we all kind of elect whoever is more active, and we use kind of a randomized backup protocol, and there's many others. Okay, so let's talk about the foundations about what can and cannot be done under this model. Any questions, by the way, on this omission model and what we want to do? Yes, Eli. Oh, I said, yeah, so in the omission model, so in the omission model, you basically assume that you have a node, a correct node, and the adversary is a bubble around this node, okay? And so this bubble, every message that comes arrives first to this bubble, and this bubble can decide either to allow this message to go through, or go out, or to block it. So the failure is on this bubble around the correct node. That's the omission model. All right, so can we solve this for any number of failures? That's kind of a question. What's the answer? No, why not? Okay, so yeah, I mean,
so you said it's a type of or subtype of Paxos algorithm, and since we had seen formal proof of Paxos, and there are mathematical understanding on how many adversaries or corrupt failed nodes maybe in Paxos case, then we cannot have more adversaries than failed nodes.
Okay, yeah, that's a reasonable answer, and okay, I won't go more. I'm just saying I'm cheating you a little bit because there are details about when this impossibility actually holds. So, but yeah, you're right. This is kind of a Paxos type approach. You can see the Dwork, Lynch, Stockmeyer paper for a lower bound. You can see my block, and this is also going to be in an exercise if you want to do exercises. So for simplicity here, we're going to assume that the number of servers we have is 2f plus 1, right? That's kind of the least number of the best type of fault tolerance we can get, right? Okay, so we're doing math. So here's the only math you will need, roughly speaking. So this is quorum intersection, otherwise known as the pigeonhole principle. And so given a set of n elements, if you have two subsets of size n minus f, how many elements do they intersect on? 1, f plus 1, n minus f, n minus 2f. Who agrees with n minus 2f? Who says n minus 3f? n minus 1f? Just f. Okay, so it requires some work. So this is another type of exercise, but again, it's a pigeonhole principle. But the correct answer is n minus 2f. So again, if you have two subsets of size n minus f, then they have to intersect in n minus 2f points. And here's kind of how we're going to concretely use this. So we're concretely use this by basically saying this is quorum intersection property, right? This basically says that if n equals 2f plus 1, and you choose a majority is f plus 1. So if you choose any two majorities, they have to intersect, right? If n is 21 nodes is like 10 plus 10 plus 1. Then if you choose 11 and I choose 11, they have to intersect somewhere, right? Because there's only 21 elements. That's the pigeonhole principle, roughly speaking. Okay, and The more complicated version is going to be 3f plus 1. It's going to be in later slides. And again, if you choose a quorum of 2f plus 1, I choose a quorum of 2f plus 1, then we have to intersect in f plus 1 elements. All right? That's kind of the only fancy math that we're going to use today. Not a lot. All right, so we're going to try to build a protocol and see what's going to be wrong. So client sends asks for a command. Let's say the command is add x to the state. And obviously to make it non-trivial, then different replicas might hear different clients, maybe in different orders and so on. And the primary, let's say, chooses the first command he hears from the client, and he wants to commit that command. So here's an algorithm. The primary just commits that command, and then he says, well, there's failures. Maybe I'm failed. So what I'll do is I'll send I'll send everybody else a message commit. Okay. So again, that's my algorithm. My algorithm is I receive a message. I'm the primary for this view. I receive a message. I commit it. I send to everybody else. Let's commit. Is that a good algorithm? Yes? No? No. Okay, why not? Yeah, so you can fail and never be able to send messages. Like maybe you think you've sent it and you didn't, right? So here's a better approach. Let's do the following. Instead of first committing and then sending, let's do the opposite. Let's first send the message, right? Because then I know that I'm only committing after I sent the message. Okay, that's better because now if I stop in the middle, at least I didn't commit myself. So is that good enough? So what I do is I'll send everybody a message, and then only then I'll commit. Is that good? Exactly. So the problem is that the primary might be omission failed, and he does not know about that. So the fact that he sent the message does not mean that he is guaranteed that this message actually arrived. So what's the simple thing that we can do to guarantee that the message arrived? Get acknowledgements. Get acknowledgements. Get acknowledgements. I need to get acknowledgements for everyone. Did you get the message? Okay, so if I get acknowledgements, I know that so this is what we do, right? So really, what is the main challenge in these protocols? The main challenge is a leader that's faulty, that manages to commit to some value, and then that information is lost, and the next leader commits to a different value. That's the main challenge. That's what we're going to solve, and we're going to solve it by, sending acknowledgements. All right, so let's go. So what we want to do is, after we send acknowledgements, we want a way, if I'm the second leader, I want to make sure that if the first leader committed something, then I'm not going to make any mistakes. Okay, so this is kind of what I want to make sure. And to do that, I'm going to run what's called a view change algorithm. And this is what I want to do. What I want to do is I want to verify that if there's any chance that the previous leader committed on something, then I'm not going to do anything that's different than that commit, because then I'll break safety. So that's kind of the goal. And there's 3 challenges to that. First, you want to make sure that the value that you're committed is persistent. And the way we're going to do that is by sending messages to everybody and getting acknowledgements. That way it's kind of persistent. Second is, when I do a view change, maybe the information is persistent, I might choose the wrong value, because maybe there's a few of them and I'm confused. So, let's make sure I choose the right value. And, third challenge is, I actually want to make this protocol live, right? I don't want to be stuck. So, if maybe there's failures and so on, so I want to get liveness in this view change. Okay, so here's kind of the high-level detail. This is kind of an important message about all the primary backup protocols that we have. I'm just checking time. Yeah, so most important thing is we're splitting this algorithm into 3 parts. So the first part is what I'll call a normal case protocol. This is when there is a primary, and this primary is pushing commands and committing them one by one. The second part is a protocol that triggers a view change. So the problem is that I might think I'm correct, but actually, I'm omission failed. And so there needs to be a mechanism to throw me away, to move from one view to the next view. And that's going to be the view change protocol, view change trigger protocol. And this is a way to replace the primary. And note that because of failures, it might be that the reason I'm not receiving messages from the primary is because I'm failed. So you have to make sure that this view change trigger doesn't throw away good leaders as well, right? So that's kind of a little bit of trickiness to do this view change trigger. And finally, the third component is the view change protocol. The view change protocol is this protocol that we're doing after we decide to move from view V to view V plus 1, and we want to make sure that we only choose safe choices. If there was a commit, we don't want to commit on a different value. Okay, does that make sense? So that's kind of the structure of these protocols. They have 3 parts. And what I want to do now is just start with kind of the normal case of a primary backup in the emission model. So, again, what happens is the following client sends appends, and I'm the primary. What do? So remember, I can't commit. What I want to do is I want to send this kind of protect myself in order to make my command durable. So I'll send this propose. So I'll send I'm proposing X, and I also say in which view. So it's view V. And as suggested here, what replicas do is they receive my message and they acknowledge it. So they send back an acknowledgement to the replica. And they do that unless they already know of a higher view, right? So I'm in view V. If they're kind of locked in a higher view, then they don't send me an acknowledgement. And what the primary does is it waits for a quorum of n minus f, in this case, f plus 1 acknowledgement messages. So I just want to show you, here's how the algorithm looks. There's a client. It sends it to the primary. The primary sends messages to everybody. The replicas, here they are. They send an acknowledgement back to the primary. Okay? That's it. That's an ACK. Propose. No, hold on. We didn't commit yet, but we're going to commit soon. So now, at this point, you can commit. This is your commit point. At this point, I claim that the transaction was committed. And indeed, this is kind of the next thing is the primary, and now we're moving to what's called learning. So in these protocols, there's always kind of a committing phase, and there's who asked the question, sorry? Yes. Is a learning phase. The learning phase is when the goal of this primary is to tell everybody, hey, this was committed. Okay? And so, you can do many things. You can send this back to the client. You can send this to the replicas. You can do it as a piggyback to the next command and so on. So there's many choices, but all right, so this thing can continue on for many commands if we need to. Every command will just be kind of, primary sends another command and so on. All right, so now we're going to do view change trigger. So what happens if, we're unhappy with the primary? So obviously, if the primary is failed, we can throw the primary away, and we have to because you might not be sending messages, and when we lose liveness, right? Remember, we wanted to get termination. There's 2 high-level approaches. One is a stable leader, and in this case, we'll keep this primary working all the time. Now, maybe this primary doesn't have anything to send, so he'll send kind of a heartbeat message. So he's going to send a heartbeat message saying, I'm the primary, I'm all okay. And if a replica doesn't receive a heartbeat from the primary, then it'll say, hey, this primary seems to be not responding. Any questions? All right. And if you hear, the problem is that, I might not hear the primary because I'm failed, but if f plus 1 people are complaining that the primary is failed, then what do we know? Definitely missing the heartbeat. So maybe it's asynchronous and we're missing the heartbeat, but most likely the primary is failed or we have a good reason to do a view change. And so if you hear, I don't hear the primary, or if you hear one primary down, then what you do is you move to the next view. You stop acknowledging these views for for view V because that would break safety, and you also send primary down to all, right? So once you have f plus 1, you can boost it to kind of a higher level message. And that's kind of that's a view change trigger, and we can do other things. So for example, we can even do this view change. Yes. Yes, you're right. Yes, thank you. Good point. Yeah, it's a mistake here. Yeah, good point. So you can do the same thing and do this trigger every round. So here, this is kind of the stable leader approach, where as long as the leader is okay, I'm going to continue sending messages. I'm going to continue allowing this leader to work. Maybe I'll let him work for an hour or for a minute, and so on. In the revolving coordinator approach, every time you commit a message, will change the leader, right? So it's kind of a way to get a leader, and there's mechanisms to do that, you get some sort of better fairness because now everybody gets to be leader, but you also have more challenge because now the clients have to figure out who the primary is, so maybe you're sending more messages and so on. So there's trade-offs. I won't go into it, but these are 2 different approaches. All right, so we've done the view change trigger. We've done the normal mode. Here's the algorithm, right? Don't forget the algorithm. That's it. And now we're going to do the view change. View change is kind of the core, typically the core non-trivial aspect of this protocol. Okay, so what do we want to worry about? So we want to worry about maybe the primary committed and then he failed. Right? So if this primary committed and then failed, then we have no way to know that it committed or not. So we somehow want to maintain safety. Maybe not this primary committed, but since we're moving to views, maybe we move from view v to v plus 1, but maybe view v minus 10, there was somebody who committed, right? So it doesn't have to be the previous, it might be some even older primary that committed. And so what this means is that sometimes the primary doesn't have to take the value from the client. It actually has to adopt a value that it heard previously. Okay, this is kind of this idea, a core idea of view change is that when you become a primary, even though you have messages you want to commit, you might be forced to commit other messages. And we'll call this an adoption. You adopt a previous leader's value. Yes, Eli?
I didn't understand that you already have a leader. New leader may need to adopt. Okay? The new leader is really the tough part of doing consensus, because in the previous one, we assume the leader only that in the case that there will be a problem, so we have something stable.
No. So again, this is primary backup. This is primary backup. This is not Paxos. This is like the list of primary backup, which means that in view 1, who's the leader? Number 1. In view 2, who's the leader? Number 2. In view X, the leader is X mod N. Very simple protocol. Okay, very simple. Yes. We'll do later more. Like that's another angle, and it's easy to fix.
So I just wanted to ask: is what's on the whiteboard? That's the second phase of view change replication.
No, we didn't do view change. This is the leader-based protocol.
Yeah, so that's telling them to commit, and then so is that telling them to commit, and then.
So at this point, the only person who knows that there's a commit is the primary.
Yeah.
And what I didn't draw here is the primary can then send a message to everybody else saying, please commit. He has a proof of commit, and he'll send a message.
So could you not lose your value then if you commit locally and then tell a client and then crash? Could you not lose that value?
Yeah, that's why we want to make sure that's the magic of view change. Exactly. Okay. So that's what we want to fix. And this is where quorum intersection comes into the rescue. This is where kind of, the math works. And the idea is the following. If the primary, before committing, somehow wrote its values to a quorum of people, then potentially, if I read from a quorum of people, I will intersect that value and I will use that value. So, is it safe to do this reading from a quorum? Yes, because of this quorum intersection. And is it live? Yes, because again, this quorum intersection, reading from a quorum is good even if there's F failures. And this is kind of the core idea. The next slide is going to explain it rigorously, but here's the intuition. Again, the intuition is the following. I'm the new leader, this is the old leader. The old leader crashed, we don't have any information. But now, what do we know here? What did he gather here? So he gathered a quorum of values, right? This is F plus 1 values. This part is F plus 1. So there are F plus 1 nodes who receive the proposed message. So that's what I will do. Okay, I will read and ask everybody for their proposed message. And so when I read from a quorum, I will intersect with at least one guy here. And that's why I'm going to be safe. Okay, that's the core, that's it. That's the only trick in view change. So here it is, here's the algorithm, it's very simple. Okay, so I'm the new primary for view v plus 1. What do? I say, hey, we're moving to view v plus 1. Please send me your highest proposed value. And what a replica does is it responds with, here is the proposed value with the highest view that I've ever seen. So, for example, maybe there wasn't a commit here. This can run for several views. Not every backup sees all the proposed messages. Maybe I saw proposed messages in views 1, 3, and 7, and you saw proposed messages in views only 13. So you will send to the primary in view 20 only 13, and I'll send only 7. So every backup sends the highest proposed it ever saw. That's it. If you haven't seen any proposed, you send some null empty message. Okay, you say, I haven't seen any proposed. Okay, what do I do as a primary? So how many do I have to wait for? A quorum, f plus 1, yeah, a quorum, right, n minus f, because, again, I want to have a read quorum hit the write quorum. Now there's a lot of values. What do I do? Which one do I choose? The maximum one and propose it again, yes. So I choose the maximum one. Why? Well, when you go over the safety proof, you realize that that's the only thing you're supposed to do. You choose the maximum proposed value. So again, you hear all the proposed values, and what you do is you adopt the proposed value associated with the maximal view number. What happens if all the quorum that you talk to say, I have no propose? What can you then do? You can propose your own value, or in this case, propose the value you heard from the client. Yeah, so in this case, you use your own value, and you're fine. That's it. That's view change. Yes? Yeah, so, here again cheating, but let's imagine that this client is sending to everybody, or like maybe sends to this primary, times out, and then sends to the next primary. So there's some mechanism that you receive it. And so abstractly, the way I'm abstracting is saying every primary has some client messages. Maybe you have some, I have some. And so you're allowed to choose whatever you want. So in this case, I'm abstracting the client away. Yeah, I mean, here's what PBFT does for the standard approach is, you hear who the primary is, you send it only to the primary. If there's a timeout and you don't get a commit back, then you send to everybody. And then when you send to everybody, either they tell you, hey, we switched primaries, or if you're still concerned, you can continue going into the broadcast mode. Typically, you don't want to be in the broadcast mode all the time because that spends a lot of messages. But there's different trade-offs here. It's a whole aspect I'm ignoring. Yes?
As far as I understood, one of view triggers you proposed was each round to change the leader. So in this case, the leader will always resend the first message.
Unless it's committed. Yeah, so what I didn't explain here is like how you terminate this. Like there's no termination here, we continue ad infinite. So obviously there's a learning phase. Once there's a commit message, you can send with the view change saying, hey, look, I committed. So I'm abstracting that away too. Okay,
thank you.
If you're building a state machine replication, you just chain the next command in. So you just say, here's a new command. But you're right. Okay, this is very important that everybody understand this. So I want to take questions, because essentially you're seeing here, this is the normal case protocol, this is a view change, and this is essentially Paxos, right? This is a version of Paxos. Yes?
Just to clarify, so in this case, does the new primary also include itself in the, does it include its own potentially last proposed scene?
It chooses the highest one. If it has the highest proposed, it uses it. If it has an older proposed, this is unlike Raft, right? Raft says, if I'm a leader, I have to be the most recent one. In this version, you don't have to be the most recent one. You adopt the most recent value. Okay?
Yeah. A little bit of a cheating to say that this is Paxos, because the moment you say...
It's not Paxos. I will call this primary backup inspired by, yes. Good. So let's do a quick, so this is the protocol, and let's do a quick sketch of why, let's prove its correctness, okay? And not prove, but I'm giving you a proof sketch. So safety, safety, this is, again, standard safety approach that we're going to see over and over again. So we're basically choosing the first view where somebody commits. So let's say if this was view 10, and this is the first time some primary commits, then view 10, that's going to be V star. So V star is the first time somebody ever commits. And then there's two things to prove. So first of all, you want to prove that in this round that somebody committed, you can't commit on two different values. Okay, it can't be that I commit on X and you commit on X prime. Okay? Why is that? Yeah, I mean, here is really easy because there's not even a Byzantine adversary. So the leader always sends only one type of message, right? So it only sends one value. So it's kind of trivial in this case. But later on, it's going to be a little bit more complicated. But really what we want to prove, and this is the main safety statement of all these protocols, is a proof by induction that says that for any view later, after V star, if any primary adopts a value, it must adopt a value that is the same as the value committed in view V star. Okay? So again, any primary for a later view must adopt this value. That's what we need to prove. So, let's do a simple, proof by induction. You assume things work, let's say, for round V. Let's prove it just for round V plus 1. Okay? So here's round V. View V is this is view 1. And now we're going to okay. I apologize for people in the back. So now, here's primary 2. And it's sending this view change message, right? It's sending view change message to everybody. And what do they respond to? They respond to with the maximum, this is the view change ACK. They respond with the maximum proposed that they've ever seen. Okay? So what do and this is, let's say this is view 2. So what do we know here? We know here that I have to wait for f plus 1 values before I continue and propose a value. And at this point, as primary number 2, I do this round, right? I send a message. This is my propose. Right? So this part is exactly the same as this part. Right? So I'm just doing, again, a view change before it. So what do I know? Why is it safe? It's safe because here I'm reading from f plus 1, and here the previous leader wrote to f plus 1. Because of quorum intersection, I know the following. Either some nodes saw a propose for view 1, or they have kind of a default view 0. So what do I know here? I know for sure I will hear this view 1 message. Okay? And so the only way I can continue is if I would adopt the right message. So that's kind of, that's the kids' version of doing induction. You just prove that it works from 1 to 2. And, it's the same type of logic will move from arbitrary view to the arbitrary next value view. Yes, Eli?
If you assume a synchronous system, then I know, okay, now round 1, I'm in process of 2, now round 1 finished, so I'm the leader of round 2. But if I suspect that it's an asynchronous system, if it's a system that can fail, which means can be somewhat asynchronous, how do I determine that now it's my turn? When is so I can determine that it's my turn if I also communicate with others and we essentially synchronize the system. What's called synchronizing.
Yeah, this is the view change trigger that I discussed. But I think I will go and say why did you provide? I think I'm done with this slide with the board. So why did we? Why is this a great question? Because this is actually, my point on the slide. That's why I wanted the slide. Yeah, so notice that if you look at this argument for safety, it does not talk about synchrony. So it works for asynchrony. So actually what we did is we proven that this protocol is safe even in an asynchronous environment. And this is kind of the nice thing about this argument, right? So we didn't even talk about message delays. However, if we talk about termination, here what we need to do is we need to wait until, what we want to do is we want to claim that everybody learns the message. Everybody learns the committed value. So we have safety, but maybe we just do nothing, right? So a protocol that has no termination is always safe. So you want to actually make progress. And so, what we want to do is the following. If a primary is faulty, we want to prove that eventually this primary will be replaced. That's one thing we want to prove. And the other thing we want to prove is that there's a non-faulty primary, and this non-faulty primary will cause termination. And to do this, we have to rely on synchrony. So again, this is kind of the primary backup approach, the Paxos approach, which says that we are safe in asynchrony, but we get liveness when the system becomes synchronous. Okay, so I won't go into how it's done, and as Eli said, there's a little bit of nuance here that we have to actually, I have to know when the system is synchronized that I am supposed to be the leader now. So you have to have some mechanism to kind of synchronize all these views, and you're absolutely right. But this is doable, and this is going back to the view change trigger. Okay, and I mentioned partial synchrony, it's very important, and so have you heard about partial synchrony? You raise your hand if you have. Okay, great. So I'll do this very fast. So asynchrony is when the adversary can block messages at any arbitrary amount of time. Synchrony, when there's some known value delta, and the adversary can send messages and delay any message between any two parties by at most delta. Okay, that's kind of synchrony and asynchrony. These are two most important models of distributed computing. And partial synchrony is kind of this beautiful in between, which says that the adversary can delay messages by any finite amount. That's exactly asynchrony. Until there's some event called GST, Global Stabilization Time. And at that time, things change. And from there on, the system becomes synchronous. So at that time and on, the adversary can delay messages only by some known finite amount delta. So essentially, what partial synchrony says is the following. The system is asynchronous until some unknown point in time where the system starts becoming synchronous. Okay? And this is kind of the algorithms in the partial synchrony paradigm. They are always safe, and they provide termination or liveness when the system is in synchrony. And this is kind of a very important approach. It's been highly successful in industry, so you've seen Paxos and Raft, and all the blockchain protocols that are out there are using kind of this type of partial synchrony model. All right, so what we've done now in 45 minutes is basically Paxos, or Eli won't call it Paxos, but I will call it primary backup replication in the partial synchrony model. Okay, so it's a relatively simple protocol. If there's no questions, what I want to do now is move from omission failures, which is what we've done now, to Byzantine failures. Yes.
On one of the previous slides, you used the word honest for some of the nodes. But if these nodes are not Byzantine, what may honest mean in that case?
So that's just my bad slide in preparation. So malicious or failed or corrupt, that's one part. And honest, non-faulty, non-corrupt is the other side. So these are just two. It's binary. I just use Yes, exactly. Yes. Yeah, I will try to make it more uniform. It's funny, some papers use these types of, some people use a different type of notation, and I probably made a mix salad. But yeah, exactly. Honest is just not. There's no bubble around me. Okay, in the Byzantine model, there's no bubble. When you corrupt a node, you actually control everything in this node. That's kind of the difference. So previously there was only a bubble where I can block messages, or I can block messages coming in or coming out, but I can't change the core of what messages are sent. Now if I'm a Byzantine adversary, I can actually send different messages. I actually control the private key of this node, right? So I can sign different messages. And so, fundamentally, what are the two big problems from moving from omission to Byzantine? So the first is if you have a leader that actually tells different people different things, right? I tell Peter, let's commit A. I tell Eli, let's commit B. So I will try to confuse them. This is how I will cause a disagreement. This is how I will cause a double spend and all those things. And the second thing that we'll have, since we now are experts in kind of primary backup and view change, is remember the other thing that needs to maintain safety is adopting the correct value after a view change. And so the other way a Byzantine adversary as a primary can cause a system to break is by not adopting a safe value. And so we're going to have to deal with those two things: equivocation and incorrect adoption. All right, so here's how we're going to do it. So what we're going to do is the following. To solve the first problem, we're going to add a subprotocol that will force the primary to act as if it's an omission adversary. It's a very classical approach in distributed computing. You have a hard adversary and an easy adversary, and you do a reduction from the hard one to the easy one. Okay, we're going to do that. Make sense? Okay, the second one, we're going to add a subprotocol that will guarantee that the primary will not make progress if it chooses unsafe values. Okay? So we're going to talk about that too. And what I want to say is the following. there are two ways to obtain this. One is if we actually introduce synchrony, so we have a synchronous protocol, and then we get synchrony, then our safety depends on synchrony, and we have kind of a quadratic communication. And then we can get a synchronous protocol for the same number of failures, n equals 2f plus 1. Or the other approach, which will take in the next half an hour at least, is continue to not assume synchrony for safety. So again, we're kind of continuing to move in the partial synchrony model, but then we'll have to assume that n is larger than 3f plus 1. Okay, so in the Byzantine model, for partial synchrony, we need 3f plus 1. Okay, so at this point, we have two choices. We either assume synchrony for safety and maintain 2f plus 1, or continue in the partial synchrony model and get 3f plus 1. So I'm going to start with this second, and depending on time, I'll move to the first one. Mm-hmm. I will show you. It's a different...
Without less than third. You still need less than third to do the transformation.
No. It's a different... I will show you. It's a different transformation. I will show you. Don't worry. I will show you. Okay, so now we're moving on the second version, which is this partial synchrony. So we're going to do Byzantine... Should have said something else. It should have said primary backup in partial synchrony. Okay, so partial synchrony again, Dolev, Dworks, Lynch, Stockmeyer, highly recommend to read this paper. Again, this is kind of the definition of partial synchrony. It's asynchronous until some point in time where it becomes synchronous. We're going to assume an authenticated setting. So authenticated setting means that there's a PKI between all the replicas, and clients send messages that are signed. The adversary controls corrupted nodes, and again, when it means it can do whatever it wants in these nodes. Yeah, you're right. Yeah, sorry. Yeah, so over here I cheated, if that's what you're saying. Over here I cheated because this should be authenticated. Yes, thank you. Yes, you're right. Absolutely. Yeah, so... yeah, as I said, there's two things you want to worry about. One is that the leader equivocates, and the other is that it adopts an unsafe value after view change. So let's solve. So can we do this with 2f plus 1? The primary can equivocate. This is kind of the asynchronous split brain approach. Again, this lower bound in DLS. If I had time, I would do it here on the board because it's the intuition is very nice. But I'm going to skip it for later. Well, actually, I will just say, yeah, so you can find it in my blog post anyways. I'm just going to erase this for preparation. No need to. Okay, so no need to. Yeah, so, okay, good. So let's do it. So what we're going to do is we have a primary that might be Byzantine failed, and we want to transform its send to all to a send to all that's like omission. So remember in the previous algorithm that we had, the potentially omission leader sent a proposed message to everybody. So now we want to somehow do a transformation that will cause a Byzantine leader the same effect. So the same effect means if I'm omission failure, I might send propose to some of you, not to all of you, but I cannot send a propose for X to Eli and X prime to Peter, right? I have to kind of send the same message. So that's our goal. How do we do that? Any ideas? We exchange between us. If we exchange between us, that will cost us quadratic cost. Can we do it in a linear cost? Yeah. That's why it says linear version. I had actually one. If we had more time, we would do. Yeah, so messages, let's say, so it's asynchronous, right? So only messages are important. Cryptography, yeah, we're an authenticated setting. So, So here's the thing, right? If Eli has X and Peter has X prime, they don't know, they might not know that. But suppose that the only way Eli could receive X prime is if he received F+1 messages, a quorum of messages. And the same thing with Peter. Then we have a quorum of people saying X prime and a quorum of people saying X. Now what happens? We have quorum intersection. Right? So it's the same thing. So what we'll do is instead of sending a propose message, we'll send pre-propose. So pre-propose is just a message before propose. Okay? And what do? So we send a pre-proposed acknowledgement back to the leader. And we send it only to the first message we hear from the leader. So if the leader sends both X and X prime, and you're a replica, what do you send back to the leader? Only the first one, yeah, only the first one. This should have been, so all these things, think about them as if they're authenticated. So you sign them. So these brackets are as sending a message. And what does the primary do? It gathers n minus f, or pre-proposed messages. Remember, here in this case, n equals 3f plus 1, so n minus f is like 2f plus 1. Okay? So, same. It should have been primary everywhere. Yeah, my mistake. I will use them interchangeably. In the authenticated setting. Okay, so you gather these things, and then you send a propose. And what you do is you add to your propose a proof. And what does this proof contain? It contains the n minus f signatures of all the pre-proposed messages. And here's the rule. The rule is, if you as a replica see a propose with a proof, and the proof contains all the right signatures, then you accept it as if this was the omission leader message for propose. Right? So this is kind of the way we move from Byzantine failure to omission failure. So is of size n. Yeah, the message is size n unless I'm using threshold signatures and then it goes back to constant size. Yes. So if I use threshold signatures, then this goes back to size, constant size. So again, here is the protocol. I'll try to draw it very big. There's nothing interesting. It's the same diagram. It's just, you send a pre-propose to everybody. No, that's the algorithm. Oh, you can do whatever you want, yeah. But I'm saying you receive this thing, you wait for, so let's hear, this is n equals 3f plus 1, just for simplicity. So this is 2f plus 1. So you wait for 2f plus 1 signatures, and then you send that message. That's going to be your propose. So if you remember, this propose is exactly the old propose we had. After this comes the rest of the algorithm. It's not a lot, right? It's just sending back a message and saying commit. And that's the rest of the algorithm. But remember, this part is the beginning of the previous algorithm that we've already solved, the previous primary backup algorithm for emission. What we did is we added one more round before it to make sure that if I'm a primary, the only thing I can do is act like an omission, even though I'm Byzantine. Okay, that's the plan. And if you give me back the slides, I will show you the proof. Yes. Oh, if you are not only in a authenticated setting, but you actually are in an authenticated setting where you have a threshold signature setup, then all these nodes are actually signing the same message. And then you can use threshold signatures, let's say threshold BLS signatures or threshold RSA signatures, and compress it into one signature.
What happens if the Byzantine primary, when it sends the pre-propose, what happens if it sends different values? How are those detected?
We cannot detect that something is wrong. All we can do is make sure that the only thing you can do as a bad primary is behave like an omission failure. Now, the way we will throw away an omission failure is by doing a view change. So the only thing I'm forcing you to do is behave like an omission failure. If you make no progress, we will throw you away by doing a view change.
What forces me to send identical?
Nothing. You can do whatever you want. But if you do something else, then nobody will receive a propose. And what happens if nobody receives a propose? Their timeout expires, and they say, let's change the leader.
Why don't they receive both? I send 3 proposes to different replicants.
Yes.
They respond to these proposes, with I accepted the 3 proposals, right? And they right?
Mm-hmm.
And then the signature, so they will have different responses, and I have to resend them. Right?
Let's prove that, okay? Since you see it, you're going to help me with the proof. So, non-equivocation. What we want to prove is the following. If somebody accepts a propose with some value and some view, then there cannot be a different replica that accepts a propose with a different value in the same view. Okay? So how are we going to do that? Well, let's do it by contradiction, just for the fun of it. So what does it mean that Eli sees a propose? It means that he saw how many pre-proposed signatures? N minus f, which in our case is 2f plus 1. The other one, this is better, he also sees n minus f. So one person saw n minus f pre-proposed messages signed for the value v, and the other for the value prime. Okay, so one for value prime. Now, what do we know about quorum intersection? How many people in the intersection? At least f? Plus 1, yeah, exactly. At least f plus 1. And why is that important? Because maybe there's f bad guys that will send Eli x and Peter x prime. But we know there's at least one honest person. If there's f plus 1, at least one honest person. And this honest person will not send 2 messages. Remember, because what we said is that you only signed 1 message. You never sign 2. And so that's a contradiction. And so, we make the proof. So again, algorithm extremely simple. Okay? And proof is also trivial. Good. So what we've done now, we've solved one problem. Remember, we had 2 problems. We've solved one problem, which is we had a Byzantine leader. We changed it so it cannot send 2 different messages in the same view. So what we'll do now is see the whole algorithm. And it's actually already written here, right? So there's a pre-propose, propose, and then here I commit. So let's go over it. Again, there's one thing missing, but it's fine. So the primary sends pre-propose to everybody, right? That's this part over here. You answer with, you accept the pre-propose if you're not locked on a higher view, just like the previous algorithm for emission. You check that the signature is correct, right? Maybe you don't want to accept, strange messages. And what you do is you send a pre-propose acknowledgement, right? So you send here a pre-propose acknowledgement. And after you send this pre-propose acknowledgement, what does the primary do? It gathers n minus f pre-propose x. Right? This is this part here. You gather n minus f pre-propose x. After you gather this, what do you have? You have a propose message. So you send the propose messages. And from here onwards, we're just going to run the same old algorithm you've seen earlier, right? So there's nothing new here. This is the same thing. Not showing you anything new, but still, we're just going to say it. So I send you a propose, but this time, with a propose proof, and you accept this propose. Why? Well, first of all, if you're not locked on a higher view, and if this propose actually contains the right signatures. So you check these signatures. And, yeah. And one thing that I want to say is, and so, you send a propose, and here you send a propose ACK, right? This is kind of the same protocol that we had previously. And the only thing I want to kind of mention here in blue is that you also remember what's the highest proposed message. I mean, it was implicit previously. I just want to make it explicit here. It was implicit in the omission failure because in view change, you sent the highest propose you've ever seen. So here I'm just kind of making sure if you receive a propose, you actually record that. This is the highest propose I've ever seen. You had a question? Yeah, this is the authenticated version. So we assume that all the replicas have a PKI between them.
I know it's from you in
Yes.
the model. Now you say, because I have signatures,
Yes.
everybody will send to 1. now the one will condense them and send to the rest, which will be everybody to everybody. If we don't have signature, we have a problem because this one can change things. But now, because of the signatures, we cannot change things.
Perfect. Perfect. And the only other thing I would say is that now your liveness depends on this person behaving correctly, but that's fine because we reduce it to an omission failure. So an omission failure, we're okay if he breaks liveness. But you're absolutely right. Great point. I should have said that. All right, and same thing happens again. You gather n-f messages, and this is where you commit. This is where you decide, and you have a commit proof, and then you can piggyback this. So it's the same algorithm. We just added one more round before that, and we're almost doing the Byzantine version of primary backup, but we still have to have one thing missing, which is kind of this view change. So the view change trigger, nothing important is going to change. So again, we have a timeout where we expect the leader to do work. If the leader is not doing work because he's sending messages that don't create enough signatures and so on. So we complain. I guess I'm compiling here two different talks, so I'm using different words here. But this is like a complaint. At least here I didn't make the mistake of not putting the view number. So you complain and say this view looks bad to me. And if you see f+1 complaint messages, then you can start a new view change. So this is kind of at a very high level how we're going to use the trigger. The only important thing here is that the primary has actually a proof that we should move away from this view. So previously, we just trusted. If f+1 people say, hey, there's a problem, then we trusted that that's OK. Here, I actually want to have a cryptographic proof. Again, as Eli says, instead of broadcasting everything, I can gather this proof, and then I can show to you that f+1 people are complaining. So again, I have f+1 different signatures of people complaining about this particular view, which is a reason to move to the next view. And so this is kind of how we do the view change trigger. And now I want to focus on the main thing, which is the view change algorithm itself. So remember, what is the view change algorithm that we had in the omission failure? It was very simple. I asked everybody, what is your highest proposed value? And I adopted it. That was it. And what we're going to do here, we're going to do something very, very similar. So first, I'm going to tell you, let's view change to view v+1. And I'm going to give you a proof that this is actually, you're supposed to move to the next view because maybe I'm just cheating. And, there's a good leader and I want to kind of, break your liveness. So you accept this message if it contains, the right messages, if you're not locked to a higher view. And what you do, if you move to a next view, is you stop responding to messages from a lower view, right? That's very important for safety. And after you do that, you send to the primary, I acknowledge that we're moving to the next value. And here is my highest proposed value. So in the omission model, we just sent the view and the value for this thing. Here, we actually have to send you a cryptographic proof. Because I might be cheating. I might tell you that I have some view and value, which is the highest proposed, but it was a message that was never sent in the system. So by sending you this proposed proof actually contains a proof of the pre-prepared messages for this value and view, so that everybody will be convinced this is a valid proposed message. So again, view and value is the proposed with the highest view that the replica heard. And proposed proof is the n-f pre-proposed signatures for this proposed message. And obviously, if I've heard nothing, then I just send kind of an empty proposed message. Okay, so it's very similar to the omission, just that now I'm attaching a proof. This proof is a bunch of signatures, again, can be compressed into one signature. All right, very simple. We haven't done a lot of changes. And the next thing we're going to do is, we wait. And here in the view change, we're going to wait for n-f a view change and for a timeout. And so, depending, maybe in the next, after that, we'll talk about the hot stuff version. So the hot stuff version is going to remove this need for this timeout. That's kind of the only thing we're going to do for that. So what I'm showing you now is kind of this is kind of the Tendermint version of primary backup for Byzantine, where you actually have to have a timeout in your view change. But other than adding this timeout, we're going to do exactly the same thing that we did in the omission model. What do we do in the omission model? We receive a lot of proposals. What do we do? What do we choose? The highest one. What did you say? Okay. Remember, that's important, right? I choose the max, the one that has the highest view number. And so, yeah, this is this idea that after I receive a lot of view change messages, I adopt the value of this value and view propose, which has the highest view. And what do? I send and I say, now for this new view, for view v+1, I use the same value as the one I adopted, and I'm giving you a proposed proof that's a proof that this is the correct value here. Okay, so that's the only thing I'm doing is adding another proof. And I do that, or if all the prepare messages are empty, then I can send you kind of my value. Right? So again, this is the analogy for an omission failure model where nobody has a prepare message, so I can choose whatever message I want. Yes? Mm-hmm. Yes. Nothing. You can do whatever you want. Yes.
And what if I can reuse old messages from the replicas?
So that's why we use the view number here, so it's hard to reuse them. But this is not a solution yet. So we're not safe because, if as replicas we just accept whatever the primary does, then we have a problem. Okay? Did I answer your question correctly? Okay. So here's the one trick. Yes. End. Yeah. It says end. Yeah, so it's like the worst of both. The one trick that Tendermint uses, which is kind of really made this possible, is inspired again by the DLS approach, is the following. You can do whatever you want as a leader, but if I already have a higher propose and you are sending a message with a lower propose, I will ignore you. So when you send, let's say we're in view 20. I know of a propose in view 13. I even send it to you as a leader. But you decide to be Byzantine, and you send here a propose for view 7, a lower view, not 13. Let's say the highest was 13. You choose to send in view 20. You send a propose that came from view 7, for example. Okay? I will see your message, and I will not sign it. I will not sign your pre-proposed message. Why? Because I am locked on a higher proposed message. That's the trick, and we'll see that it works. Yeah, let's say 20. Prepare. What I want to look for is propose. So I'm looking for proposes. I choose the highest propose. Yes. Yes. Mm-hmm. Yes. Yes. Yeah, but with no proof. So if it's empty, then it's like 0. It could even send something from view 7. And I claim here's our safety mechanism. The safety mechanism is when this leader sends you a pre-propose, you will ignore it because you've seen a higher propose. Yes, not the view, the current view we are. It's the value of the proof. It's the view of the proof. Okay, let's see that in the form of pseudocode. That's the only thing that we're doing. So again, here's the full protocol. Primary sends a pre-propose, but now, in addition to the value in V, it's also sending this propose proof. The propose proof is the hopefully highest propose this leader saw, but if he's Byzantine, he can do whatever he wants. Okay? Now, what do we do as replicas when we receive this message? So we accept a pre-propose. It should be here with the proposed proof if the following happens. Well, we're not locked on a higher view, so this is relative to V, right? We might already be in a different view. The value is valid, so if it comes from a client, Or in a sense, we check if it's a proposed proof, we check that the proposed proof is correct. But the most important thing is that we check this proposed proof W, and we check that it is equal or larger to my personally highest accepted proposed view number. Okay, so again, this might be in view 20. I'm a replica in view 20. Maybe the highest proposed I've seen was in view 13. If you send me in view 20 a proposed proof that came from view 7, I would ignore you. If you send me a proposed proof that came from view 19, I would accept because 19 is higher than 13. That's like 0. That's it. We're going to prove that that works. It gives you safety, but that's the only change in the protocol relative to everything else. That's why I'm going to go relatively quickly on the rest of the protocol. So yeah, after you get n minus f pre-propose x, so now they're assigned. You gather it, and now you have a proposed proof. And after you have a proposed proof, you send the propose to everybody. You accept it if you're not locked on a higher proof, and it's correct. And yeah, I don't know why it's. And you update your highest accepted propose. That's again the standard thing to do. And once the primary gets m minus f propose messages, that's your decision proof. That's your commit proof. Okay, so the only thing we've changed is that the primary is supposed to send a proposed proof, and we check this proposed proof relative to our highest value that we've ever heard of proposes. Yes?
So I was just going to ask, what's to stop a Byzantine node sending higher and higher view numbers and stopping progress?
So you have to have some cryptographic, so you have to have a proof that you're allowed to be in that view number.
Yeah. Okay.
So you have to have f+1 people agree with you.
Yeah, no worries. Thank you.
Yeah. Good point. I'm kind of glancing on the view change trigger part because I want to focus on the safety aspect here. But you're right. Okay, so nothing changed here, and now we're going to do a sketch of safety. Okay, so the sketch of safety is going to be very similar to the proof that we've seen in the omission case. Remember, there's two things you need to prove. So again, we choose V star to be the first view that any replica committed. So let's assume that in view V star, there's some replica that committed in, let's say, chooses to commit value X. All right? So the first thing we need to choose is that, so we're going to prove by induction that, if any propose is going to be consistent with this value. And what we want to prove, is, first of all, is the base case. So in the base case, we want to prove that I cannot have a propose of X and Eli has a propose of X prime. Now, why is that true? Remember, we added this pre-propose phase so that to block equivocation. So it cannot be that I have a propose of X and Eli has a propose of X prime. So the first technique we used helps us for the base case of the induction. All right? Very simple. Does that make sense? I didn't get enough acknowledgements. So again, what I want to show is that if somebody made a commit in view V star, it cannot be that somebody has a propose in V star for a different value. Yeah, V star. V star is going to be a base case. It's the first round where somebody committed. And so just for V star, is it clear that nobody has a different propose? Yeah, so you're all wondering about the induction statement, right? So anybody has maybe a hint of why the induction will work? If I committed, how many people have a propose? Okay, let's assume n equals 3f plus 1, just to make a simple description. If I committed, how many people have a propose? Two f plus 1, 1f plus 1. There's 2f plus 1 that sent me a propose. How many of them are honest? At least 1? At least 2? At least 3? At least f plus 1. So if 2f plus 1 sent me, there's at least f plus 1 that are honest. So it means that if I committed, there are f+1 nodes, honest nodes that have a propose. The leader for view 2, how many nodes does it have to in order for him to get a propose of some value? How many nodes does it have to talk to? 2f+1. These 2f+1 have to intersect with these f+1 guys, right? There has to be intersection. And that's going to be the safety, right? Because they are locked on the right value. So if I have to move with 2f+1 and there's f+1 honests, they will force this guy to move and adopt the right value. Basically, I mean, if he doesn't, he won't get enough signatures. That's the safety proof. That's it. That's simple. Okay, so yeah. So the induction idea is the following: there's a core of f+1 non-faulty, and this core of f+1 non-faulty. The reason we have it is because there's 2f+1 that send acknowledgement. So there's at least f+1 propose that are non-faulty, are honest, are non-corrupt. And they will always, again, by induction, and you have to prove this by induction more carefully, they will always be locked on the correct value, right? They might be locked on higher and higher levels, views through the induction, but they will always be locked on the correct value. And that is going to block any bad leader from choosing a different value. Because the only way a bad leader can make progress is by getting a propose. The only way to get a propose is getting n-f messages. The only way to get n-f messages is to intersect at least one guy here. But the one guy here will only accept the value that he's locked on. If he's locked on some value, he will not accept you sending a different value. And so this is kind of the safety. And so, you know, what about liveness? So here's the thing. So again, or the same thing we want to show is that if there's a non-faulty leader, and the system, which is elected non-faulty primary, and the system is synchronous, then we make progress. Remember, we're in this partial synchrony world where we're always safe. This argument previously did not use synchrony at all. So this is safe in asynchrony. But you know, for making progress, we're going to assume synchrony for now. And yeah, so what we want to do is the following. We want to make sure that a new leader in synchrony will make progress. Now, what's the risk? The risk is the following. It could be that when I do a view change, there is one poor honest guy that has a relatively high propose number. Now, what happens if I do not hear this one guy? It could be that the propose that I choose for this view is lower than the propose that this honest guy has. Okay? Now, what will happen if that happens? Then this honest guy will not sign the pre-prepare message. So I will not make progress. Okay? And so this is why the liveness here depends on synchrony. And what you can show is that if you take the same algorithm that I've shown you and remove this and just wait for n-f, so no timeout, then the adversary has an infinite execution where there's no progress even after the system is synchronous. So we completely synchronized, but every round there's like a good leader, the good leader tries, misses one guy, then has a proposal, suggests that, and the bad guys are quiet, and one good guy is also quiet, so he doesn't have 2f+1, he has only 2f. And then there's again a bad leader comes in, and then another good leader, and then another bad leader, and you're going to have kind of an infinite execution. So that's why you need this timeout. And one interesting question is, can we improve this thing? So can we remove the timeout from the view change when there's a correct leader? And so this brings us to this notion of responsiveness. Responsiveness is this property of protocols where the speed of the protocol does not depend on timeouts. It's often a beneficial thing to have. So again, liveness is obtained when there's a non-faulty leader, which is and the system is synchronous. And what we want to do is we want to avoid this property that there's one honest that can break liveness. It's the same slide. What's going on here? Yeah. So this is this property of responsiveness. It is the same slide. Where what we want to do is we want to have the system move as quickly as the network allows us and not depend on this timeout delta. This timeout delta comes from the GST model. This is the assumption on when it's synchronous. It is typically a worst case assumption, right? So let's say you say, well, every message takes 10 seconds. But we know that in the internet, messages might take maybe a quarter of a second. So why wait always 10 seconds? You can actually move much, much faster if the network is faster. Notice that we haven't yet solved asynchronous Byzantine agreement. We still have to have a timeout if there's a faulty leader. So a faulty leader can decide to not send any message, and so we'll still have a timeout. So all this tries to do is make sure there are no timeouts if there is a good leader replacing another good leader. Okay, so this is kind of the response. This is why it's called optimistic responsiveness in kind of more formal ways. Sorry, to change?
Sorry, is it possible to change timeout to number of attempts?
To?
Number of attempts.
Yeah. So you can do smart things like, if I understand the question, like do no timeout 3 times and then do a timeout in the 4th time. Or you can change the timeout to be 1 second, then 10 seconds, and 20 seconds, and so on. So there's a lot of systems techniques that you can use, which will make it very efficient even with timeouts. So I'm not saying that if your protocol is not responsive, then you're doomed. It's perfectly fine. It's just that kind of, again, from a foundational perspective, we want to get responsiveness. And there are use cases where, even with all these tricks, you might not move as quickly as the speed of the network. Okay, I can show you kind of corner cases. Okay, so here's what we're going to do. So remember, what was the problem? The problem was that there was this one poor guy that had to propose, and we missed, because we read from n-f. Maybe we missed this one poor proposed guy. And that was the problem. How much time do I have before break? 5 minutes? Okay, so this seems to be a problem that we've already solved before. So recall that for safety, we had a similar problem, right? We had a problem that one guy committed. Remember back, in the first 10 minutes of the talk, we had one guy committed, and how did we make sure that we remember this one guy committing? Yeah, we had a quorum of proposed messages. Yeah, so we solved this by adding a round that says that if an honest commits and there's f+1, they have a proposed. So the commit might get lost, but there's a quorum of people that are going to help us remember things. And we're going to use the same trick here. In the sense that what we want to do is make sure that if I have a propose, then there's a bunch of people that have evidence for my propose, and I will call this evidence a key. It's just a name. Okay, so the trick here is going to be, if you have a propose, then there's n-f people that have a key. How do we do that? One more round of acknowledgement, yeah. So as you've seen, the only thing that's happening in our algorithm is the leader sends to everybody, gathers n-f, leader sends, n-f. And so what we do is we add one more of that round, okay? I mean, the algorithm is going to change, and well, we'll see in terms of time how we want to do this. But yeah, let's go over the algorithm. So what we're doing is the following. We're just going to add one more round so that instead of, this was the prepare round, and this is the propose round, we're going to add one more round here in the middle. So sometimes I have a larger board, but I will conduct a surgery here. So we will replace, so between the pre-prepare is going to help us for non-equivocation. We want non-equivocation anyways. And the propose is going to help us for safety of the commit. But now we want to somehow make the propose not go away, so we add one more round. So I will kind of shrink this piece so that it's smaller. So it didn't change, it's just shrinking. And now we will add one more round. Maybe I'll do it in a different color. So in this round, we send messages, and then we gather the messages back. And this is going to be the key phase. So the only thing that's happening is the following. This first step, step 1, is pre-prepare. This gives us non-equivocation. This second step is this new phase, key phase. This gives us the fact that if anybody has a propose, there's a quorum of people that have a key. That's going to help us not miss this single propose when we do a view change. And finally, we have the same thing. After we have a quorum of proposes, that's the commit. So we just added one more round to the protocol. Okay, so let's do this in the pseudocode. Yeah, so remember, you send a pre-propose, and now in order to kind of prove that you're making progress, you send this key proof. So it's not a propose proof, it's a key proof. I will explain why we kind of moved from a propose to only having a key. And well, you accept this over here, this phase, and it's the same thing that we had earlier, right? You're not locked on a higher view. The message is valid. And the important thing here for safety, remember, is that you do not accept this proof if you are locked on a higher value. So here is kind of the trick, or one trick, which is you compare the lock proof that you receive from the leader with the highest propose you have. Okay, so you are locked on proposes, you compare that to the key. Okay, there's two different phases. And okay, if that happens, then you send a pre-propose ACK. This is this phase over here. And now, instead of just sending a propose, then this is just kind of a bug, I guess. Then you send a key. So what you send is a key message with a key proof. This is this message over here, and then the replicas send back they accept this key proof if it has all the pre-prepare messages. Something gone wrong here. But anyway, at this point, they update the highest accepted key, and they send a key ACK back. So this is exactly what's happening here, right? You send a key messages, and you update the highest key. And then you gather n-f key ACKs, and this is your signal to create a propose message. So previously, a propose message was from n-f pre-propose. Now a propose message is from n-f key messages. We just kind of added one message, one type of message in the back, in between. And again, the messages, this part remains the same. We send a propose, and if we have n-f proposes, then we're kind of we have a commit proof. I have to fix the order here, and this is kind of where, yeah, you gain n-f propose messages, and this is where you commit. So before we stop, I want to kind of see if there's questions specifically on this protocol. So what I haven't shown you is the view change part yet, but this is kind of the normal case.
You said that loss of one honest replica could lost liveness. Mm-hmm. So it's a possible situation when we lost one replica. Should we adjust our numbers? When we lost a replica, then, for example, we don't have enough responses. We initiate view change. New leader doesn't have enough replica. Initiate new change view. We should adjust.
So
numbers.
Previously we could not. We were stuck. But here's what's the new power we have. If I'm the poor guy that has a propose, maybe you're the new leader. You won't see me in your view change. But you read from n-f, that n-f has to contain f+1 honest people that see the key. So you might not see my propose, but you will see at least one key. And so you as a new leader will use that one key, and so I will be happy. That's the trick. Okay? That's kind of what I wanted to say in the next slide, but that's the main trick. The main trick is, again, I will still be able to miss your propose, but your propose is backed by f+1 honest keys. So when I do a view change, I will read the highest keys, not just the highest locks. And I will use these keys in order to send a message that you will be happy with.
I need to think about it.
Okay. All right, so yes.
Okay, so one last. So will you told us later how these keys should help us when we change the view to keep liveness, yes? You told us later? Or?
Well, we didn't do the view change, but in the view change,
Yeah.
I mean, I will say it again slowly. The main problem is if there's a good guy that has a propose. I might miss him because I hear from only n minus f. I do not wait for this one good guy. But now, since we have these keys, if he saw a propose, there's at least f plus 1 honest nodes that saw the key. The f plus 1 honest nodes will intersect my 2f plus 1 view change quorum with at least 1. So as a new leader, as a new honest leader, I'm guaranteed to see the key that you use as a propose. And so I will adopt a value that you will be happy with.
Okay, thank you.